Hello everyone and welcome to MV Tutors. I'm Tulu and today we're going to cover the lesson on electrochemistry, okay? Particularly electrolytic cells. So you guys are in matric this year, or some of you are actually upgrading so that you can get to study whatever you want, right? And you don't have the hindrance of physics marks in the way. Okay, so yeah, we're going to start with electrolytic cells and let's get right to it. All right, so first of all, we're just going to define some terms. All right, then I'm going to sketch the electrolytic cell. We're going to label it so that you understand what is going on. And then we're going to go to the applications in industry. Like, what do we use electrolytic cells for? Why are we learning about it? Like, why is it so important? Okay. All right, so we're going to start with electrolysis, just defining it. So basically, electrolysis is a process, okay? It is a chemical process since we're dealing with electrochemistry. So it's basically a chemical process where electrical energy. So in order for the chemical process to begin, we need to power it up, okay? So yeah, it's a chemical process where electrical energy, just gonna, yeah, electrical energy is converted, okay? It is converted, or you could say it produces chemical energy. Okay, so that's pretty much that. So what happens then? You use an electrolytic cell. You use an electrolytic cell to ensure that that process goes on. So at the electrolytic cell, basically you have electrical energy converting or producing chemical energy. Okay, and then I have these letters here, aura and rock. Okay, so that's my way of really remembering what's happening where. Okay, so let's start with aura. So O in this case would stand for oxidation. Let me just lift that up a bit. Okay, so that's basically O for oxidation. Okay, and then R, that will be referring to the reducing agent. Okay, and then A, we talk about the anode. Okay, so in your electrochemical cell, which is the electrolytic cell in this case, where the whole process is happening, where electrical energy is used to convert to or produce chemical energy, right? So oxidation actually occurs at the anode. Okay, whether you're looking at the electrolytic cell or the galvanic cell, at the anode, that is where oxidation occurs. Okay, so please don't forget it. Oxidation occurs at the anode. Okay, oxidation is a process. All right, it is a process. Okay, so what happens? What is oxidation? Oxidation, basically, it is the loss of electrons. Okay, now you have the reducing agent. All right, so reducing agent, well, that's basically, in this case, it is a substance. We mentioned that oxidation, that is a process, okay? And the substance that ensures that oxidation occurs, well, it is the reducing agent, okay? Yeah, so oxidation occurs as a process, and what makes sure that this process actually occurs, it's the substance called the reducing agent. So basically, this reducing agent, this substance, okay, yeah, but I'll write it again. Basically, a reducing agent is a substance that is oxidized. Okay, yeah, it is oxidized. All right, and then all of this, it happens at the anode. Okay, so the anode, that is actually an electrode. Okay, for the electrolytic cell, the anode carries a positive charge. Okay, so it's again an electrode where oxidation occurs. And for this electrolytic cell, it actually carries a positive charge. You'll see it clearly once we have the sketch. Okay, now my handwriting is just going down, but it's fine. So anyway, at the anode, like I was saying, that is where oxidation occurs, okay? The anode is the electrode that is positively charged on the electrolytic cell. Oxidation occurs at the anode. Oxidation is a process where electrons are lost, okay? And what, I'm looking for this term, what carries this process through is the reducing agent, okay? The substance that is actually oxidized, okay? And then we get to rock. You will oftentimes hear in class or on other videos that another way of remembering this is an ox. Okay, basically at the anode, that's where oxidation occurs. So it's up to you. Either you remember aura or an ox. All right, and then we have rock. Okay, so basically R stands for reduction. Okay, O stands for oxid. Let me keep writing the. It's oxidizing agent. Oxidizing agent. And then the C stands for cathode. Okay, so basically, again, reduction is a process. You have a reduction process. And what actually makes this process happen? It is the oxidizing agent. Okay, and where is all of this happening in the cell? It happens at the cathode. So reduction, the process, basically it is the gain of electrons. All right, the oxidizing agent, well, it's a substance that is reduced. And the cathode, well, basically it is the electrode where all of this is happening. Okay, so the electrode where reduction occurs. And basically for the electrolytic cell, at the cathode, well, that is the negatively charged electrode. Okay, so it is, yeah, negative. I'm gonna say negatively charged, even though it's positively charged. But yeah, you get it, right? Cool. So yeah, that is basically what happens. And if you can't remember rock, like reduction happens at the cathode and it is facilitated. Yes, I was looking for the word facilitate. It is facilitated by the oxidizing agent. If you can't remember rock, then you can go with the red cat. So basically reduction happens at the cathode. So think about a red cat and you remember reduction happens at the cathode. If you think about an ox, then that's where oxidation happens at the anode for the electrolytic cell. Anyway, it also happens for the galvanic cell, but we'll get there. All right. So now I've been talking about an electrode, like what is happening? What is that? I've heard about it. I'm not sure. So what is an electrode? Okay, and also electrolyte, because how is this happening? How like what's happening? So basically the electrode, okay, that is, it could be a rod, okay, that you place inside an electrolyte. So we'll get to the definition of an electrolyte. But it's a rod that is conducting electricity. So a rod conducting electricity. Okay, and so it's a rod conducting electricity, and like I said, it is placed inside an electrolyte. All right, and this electrode can either be the cathode or the anode. Okay, so yeah, you either have the anode, remember, that is where oxidation occurs, or you have the cathode, where reduction occurs for the electrolytic cell. Okay, and then you have an electrolyte. So basically that is a solution, okay? It's a solution, ionic solution actually, okay? I'll put the ionic because, I mean, if it's ionic, it does allow electricity to be conducted. Okay, so it is a solution, okay, ionic solution, or you could say ionic liquid, you know, it's up to you. And basically, it conducts electricity. Okay, yeah, so like I said, it's an ionic solution that conducts electricity. And how does it do that? There has to be a movement of ions. Okay, so through ion movement. All right, so we have defined a lot of things here. And they could ask either. They like asking, you know, about the oxidizing agent and reducing agent. Please, it can be a little bit confusing where the process is oxidation, yet the substance is a reducing agent. Like, what's happening? Couldn't it be an oxidizing agent? No, no. For oxidation, that process, you require the reducing agent, the substance, to make sure that this process is facilitated, right? And everything is facilitated at the anode, okay? And the same that happens at the cathode. All right, so now we get to our sketch. So what is the anode? Which one is the anode? Which one is the cathode? For the electrolytic cell, okay, let me just choose a different color. For the electrolytic cell, you have, like we said, we are taking electrical energy and we're converting it, or it's, you know, produced, it's used to produce chemical energy, okay? So we need a power source over here, okay? Whatever power source you can get, okay? The thing about sometimes electrolytic cells or electrolysis is that because we require electricity to get the chemical reaction going, it can be quite an expensive procedure. Okay, so yeah, and I mean, in a country like ours where, you know, electricity can be a little bit unstable, especially if ESCOM is the source of providing electricity, then it becomes a bit of a challenge, okay? It is also expensive because currently we are very dependent on coal to produce electricity, and we know the problems with coal, you know, global warming and the likes, and people are trying to move over from that to solar energy, wind energy, and all of that to produce electricity. So this can be quite an intensive procedure, but it has to be done, okay? We just don't have a choice. We have to do it. So we require a power source, okay? Then you have, on the left-hand side, I've actually put there, let me use another color. So that would be the anode, okay? So the anode is there on the left hand side, and I did say that the anode is positively charged for the electrolytic cell. Why is that? It is because it is connected to the positive terminal of the battery. Okay, sorry about that. So it is connected to the positive terminal of the battery. Okay, so this would be positively charged. Okay, if it was left to itself, let's say there was no power source and some form of reaction had to occur, the anode would actually be negative. And I'll explain that once we get to the galvanic cell. But because we are forcing matters here, we have a power source, we're directing how the electrons should flow, and you know, the charge on the anode, in this case it is positive, okay, purely because it is connected to the positive side of the battery. All right, and then what else? So we said at the anode, that is where oxidation occurs. And what is oxidation? It is the loss of electrons, and that's why you see here electrons are busy escaping, okay, going from the anode all the way to the cathode. Okay, so if this is the anode, okay, then the other one definitely has to be the cathode. So you have electrons that are leaving, because oxidation by definition means that you are losing electrons, okay, and it wouldn't have happened unless you have this electrolyte in here. All right, so this is your electrolyte, the solution that we mentioned. Okay, and like I said, the anode is actually an electrode. In this case, for the electrolytic cell, the anode is positively charged. Okay, we also have another electrode this side, which is the cathode. Okay, let's get a different color for it. Okay, let's see, cathode. All right, so at the cathode, like we described, or we have already defined it here, that's basically the electrode where reduction occurs. Okay, reduction is the gain of electrons, and you can see the electrons are busy finding their way to the cathode. Okay, and as a result, well, because this electrode is connected to the negative terminal of the battery, its charge will also be negative. Okay, some others would remember that it is a negatively charged electrode because electrons are coming to it. Therefore, if you have a lot of electrons, then surely it should be negative. As well as with the anode, they would say, well, if electrons are leaving, then the electrode surely should be positive, right? It has to do with the power source, honestly. So because the anode is connected to the positive side of the power source, or the positive terminal, if you have a battery, then it is positive, whereas the cathode is connected to the negative side, so it is negative. Okay, so now you have an electrolyte. Okay, so we talked about a solution that basically allows electricity to be conducted. Okay, so in this electrolyte, you would have an ion, or rather, let's say you have a salt in there. Okay, and once the salt comes into the solution, it would dissociate right into its ions. You have positive ions, and you also have you have negative ions that are in there. Okay, so if that is the case, I'm just gonna put x's and y's. Okay, so let's say you have, I'll put the x's as positive. Okay, so you have your ions in there. And then you have your other ions that are negative. So the positive ones we call cations, and the negative one we call anions. So you have your negative ions in there, which are anions. So this forms part of the electrolyte. So when you have these ions at this ionic solution, it allows the flow of electricity. So it conducts electricity quite well. So what basically happens then is, once you have all of this happening, you've switched on your power source, electrons are starting to leave the anode, they are going on the side of the cathode, and you have your electrolyte in there. Okay, so what would happen is your electrolyte, the positive, the cations, will actually want to attach themselves to the cathode, because the cathode is negatively charged, right? And then opposites do attract. So you would have your positive ions, your cations, actually migrating or going all the way, attaching to your cathode. Okay, because it is negatively charged, and we know that opposites attract, so it will go all the way and attach itself to the cathode. And then you would have your negatively charged ions called anions, and they will basically attach themselves to the positive electrode, which is the anode in this case. So that's basically what you would have there. Okay, and this Y basically there. Okay, so now as these cations are going all the way to the cathode, they will be reduced. Okay, and as well as these anions, as they're moving to the anode, they will be oxidized. Okay, but here's one thing about the electrodes, right? So as we're going to talk about the application of electrolysis, it will start to make sense. But once this process is actually happening, this electrochemical process is actually happening for the anode, all right, because electrons keep leaving and finding their way to the cathode, your electrode there, the anode, will start to lose mass. Okay, it'll actually start getting smaller in mass, all right? So yeah, instead of this, it will start being eaten away, and maybe you'll be left with like this portion here. Okay, yeah, basically that. And then your cathode, on the other hand, because it's busy gaining electrons and reduction is actually happening there, it will actually start increasing in mass. Okay, start gaining weight. All right. And then you'll start seeing, when you look at the applications, like I said, why do you want that? Why do you want the other one losing mass and the other one gaining mass? Okay, I'll explain that much later. So yeah, that's pretty much what happens with electrolytic cells. This is the cell. Both of the electrodes are in the same solution, but like I said, because opposites attract, anions will go to the anode and cations will go to the cathode. All right, so now we're still going to look at different types of electrolysis, okay, or electrolysis, however way you want to pronounce it. So first of all, we look at the electrolysis of molten ionic compounds. Molten, think about lava, volcano, eruption, and then the liquid that comes, which is basically something that was solid before, and then it becomes liquid, but not as, it is highly dense. Let me just say that. So molten ionic compounds. So when you look at the electrolysis of molten ionic compounds, that's pretty much where you get that your cations will attach to the cathode and your anions will attach to the anode. Okay, that's pretty much that. All right, so negative ions, which are the anions, okay, the anions move, or rather they become oxidized, but they move to the anode. So the anions move to the anode where they are oxidized, and the cations they migrate all the way to the cathode to be reduced. Okay, so yeah, that's basically what happens with the electrolysis of molten ionic compounds. But now we get to the electrolysis of ionic solutions. Okay, this one is not so straightforward, okay, because it depends. So with ionic solutions, you normally have water. So you have a salt that you would put inside water, né? And basically once that happens, it starts to dissociate, break apart, right? And then you have your cation and you have your anion. But also, the one thing you need to think about is the water itself. It's made up of H2O. So you have positive H ions and you have negative hydroxide ions. Okay, so then now you're wondering, okay, which one exactly will go to the cathode and which one will go to the anode, because they're going to try to compete. Okay, and for this case, for the electrolysis of ionic solutions, we're going to need the table of standard reduction potentials. Okay, I'll get it out and we'll also talk about that. Okay. Oh, one thing I forgot to mention with the electrolytic cell, you're going to have a half reaction. Again, when you consult your table of standard reduction potentials, you're going to have your half reaction, okay? So at the anode, like we said, oxidation occurs, right? So what you would have, what did we have there? Let me just use, I don't know what to use now. Let's just say we have a W or U and W. So let's say we have U there, okay? And U is this electrode here. It is a solid. All right, so this solid here, what would happen is it would lose some electrons, and when it loses some electrons, you now have a positively charged ion, right? So you would then have a U plus because electrons left, so there are more protons, okay, which is an aqueous solution, and you would have the amount of electrons lost. Sometimes there are 2 electrons lost, whatever, but I'm just making an example. So you go from that solid and then it gets depleted. That's why you end up having a loss in mass, because that solid becomes depleted as it forms ions, okay, because the electrons are leaving. But on the cathode side, you have those ions there. Okay, let's just use W. You have those ions there, okay, and they are busy gaining electrons, and as a result, they are reduced to form a solid, okay, and therefore that is why it keeps gaining mass over here, okay. So as these x's come here, I should have actually just used x. X, and then it gains some electrons, so it becomes reduced. Y, on the other hand, it would lose electrons, and then it is oxidized. But basically those are half reactions, and you see that I'm actually using one arrow. All right, so please do not use, when you're consulting your table of standard reduction potentials, please do not use double arrows. You won't get any marks, okay, but we'll get 2 examples concerning that. So now we get to the electrolysis of ionic solutions. Okay, so with the electrolysis of ionic solutions, basically you would have an ion, right, in water. So you would have water, right, like I had explained, and you put, maybe for example, let's just use copper chloride. Okay, if I were to put it in its ionic equation, I have H ions, right? And then I also have OH ions. And then I have copper. Okay, so because copper 2 plus, we had to have 2 of the chlorine or the chloride ions. Okay, and then we have the chloride ions. Okay, in this case, you would put a 2 there, but that's not really the concern right now. So you have all these ions, okay? And remember, in your electrolytic cell, you have your anode, okay, which will be positively charged, and the negative electrons, the negative ions are going to go there, okay? So you have your anode there, which is positively charged. Therefore, you have either the hydroxide ion will be oxidized or the chloride ion will be oxidized, okay? Then you have, this is the anode, right? And then you have the cathode, which is negatively charged, okay? And in that case, the positively charged ions, your cation ions, are going to migrate there, okay? So copper 2 plus is going to go there to get reduced, and also hydrogen will go there to get reduced. So my question is, when you're dealing with the electrolysis of ionic solutions, you have 2 options, and not both of them are going to be reduced or oxidized. Only one of them will. Okay, so there are rules, okay? If you're going to look at your table of standard reduction potentials, the one that has a higher reducing ability will be the one that is reduced of the 2. The one that has a higher oxidizing ability will be oxidized from the 2. But there are rules as well. Okay, so let me just remove this and let's talk about what those rules are. So whenever you have solutions that water is involved, please be mindful that you have the option of the positive ion, which is the cation, and the H plus ion, okay? That will go to the cathode. And you have the also what goes to the anode, you have the possibility of the anion as well as the hydroxide ion. And now you need to ask yourself, what are these rules that I need to adhere to make sure that I am reducing the correct thing and I'm also oxidizing the correct thing. So basically, if we're going to talk about what happens at the anode, okay, basically which anion is going to go to the anode. All right, so if you're going to look at your group 7 elements, okay, group 7, you have fluorine, iodine, chlorine, bromine, but basically bromine, iodine, chlorine. Okay, so if you have those, okay, chlorine, bromine, iodine, okay, versus the hydroxide, the chlorine, bromine, iodine, your group 7 elements, they are actually going to win. Okay, this is the one that will be oxidized, and the hydroxide in this case will not be oxidized. Okay, all right. So basically that's when you have the group 7 elements. Okay, but if you have other things, maybe let's say you have your sulfate solution, sulfate ion, or you have nitric ion, hope I'm having the right one there, versus, okay, the hydroxide. Well, basically, the hydroxide will be preferred in this case. Okay, so that is what will happen if you have a hydroxide versus, your sulfate. Actually, sulfate should be 2 minus. Let me just erase that. Okay, sulfate should be 2 minus. Okay, 2 minus. So yeah, your hydroxide will be preferred in this case, and this over here, it won't be. Okay, we'll check on the table of standard reduction how it actually works, just in case you're like, okay, but in this case I don't have a sulfate, or a nitrate. So what now? Let's say you have copper, okay, and you have copper there competing, okay, but copper is positive. Chlorine, in this case, the chloride ions will win against the hydroxide. But yeah, that's basically that at the anode. That's actually what's happening. So at the anode, if you have your chlorine, bromine, iodine ions, we would say chloride, bromide, or iodide ions, they are the ones that will basically be oxidized at the anode. Okay, and what would be the product? Okay, so therefore the product would be a halogen. Okay, so your chloride would then become Cl2 and probably in a gas phase. Okay, so that's what I mean by a halogen will form. All right, and then in terms of the sulfate, nitrate versus hydroxide, well, basically we said the hydroxide will win this round, and therefore your product that will form would be oxygen gas. Okay, so it'll be oxygen, and that is what happens when you are dealing with the anode. Now let's get to the cathode. Okay, where the positive ions are drawn there. What are the rules pertaining to the cathode? All right, so what happens at the cathode? Well, basically, that bird. Okay, so basically here we will be comparing the metals, right, that are, well, that are your cations. Okay, in this case, the metal would be copper. Okay, the metal would be copper in this case. So you will be comparing the metal ion, okay, that your cation, as well as your hydrogen ion, okay, because remember, for hydrogen we had the hydrogen ion and we had the hydroxide. So we'll be comparing cations such as the hydrogen ion, okay, and here you have your copper ion and you have your chloride ion. Okay, two of them. All right, so at the cathode, it's really just comparing, or rather looking at the metal cations that you have. Okay, so if you were to look at your table of standard reduction potentials, the metals that have a positive voltage, okay, positive EMF, well, those are the ones that will be reduced, okay, at the cathode. But your metals that have a negative EMF or negative voltage, potential difference if you want, those ones, well, they won't win against the hydrogen ion, okay. So yeah, it depends. So you have to look at your metals. So the metals that have potential difference that is positive, let me put it like this rather. Let me just say, so your metals, metal ions actually, okay, the cations that carry a positive voltage, EMF, potential difference, okay, will be preferred over the H ion, okay. But if you have metal ions that carry a negative voltage, EMF, potential difference, those ones, the H ion will definitely be reduced, okay. So remember, at the cathode, that's where reduction happens, so that will be reduced, and here oxidized, okay. Please don't forget that. Aura, okay, and rock, or an ox, red cat, okay. Don't forget that, please. The one thing that I also forgot to mention when it comes to electrolytic cells is that they are actually exothermic in nature, or by nature, okay. So yeah, electrolytic cells, they are exothermic, and if you forgot what exothermic actually means, no, I'm lying, they are endothermic, sorry. Electrolytic cells are actually endothermic, okay. Endothermic, well, that is that your enthalpy is larger than zero, okay. But the EMF, I was thinking about EMF when I said exothermic, but your EMF that you calculate, it will always be smaller than zero. Guys, if you were to calculate this when you're doing calculations and you get an EMF that's bigger than zero for an electrolytic cell, there's something that you did wrong. Okay, please, please, please make sure that your EMF is always less than zero. And these reactions are endothermic. Okay, I think that's it that I forgot in that regard. Yeah, so it's always smaller than zero. Not sometimes, but always. Okay, so that's basically what happens with the electrolysis of ionic solutions. Okay, remember, water is involved. Okay, because normally if you have, in this case, copper chloride, it will come as a solid, and for you to get it to be in an aqueous solution, or aqueous state, aqueous solution or aqueous state, it will have to dissociate, but in water. Okay, so don't forget the H plus and the OH minus ions that are also competing with the ions that come from the compound. Okay, now we get to the electrolysis of water. This one, not really major. I haven't really seen it being asked about so much in exams, but we have to cover it. Okay, before we do the electrolysis of water, I wanted to actually show you guys on the periodic table which ones are actually your metals. Ah, gosh. My goodness. Okay, there we are. Okay, so yeah, let me just minimize myself. I'm taking up the whole screen here. Okay, put myself there. Okay, so don't forget, for your group 1, group 2, as well as your transition, well, this orange phase here, which is the transition metals. So group 1 would be your alkali or alkali metals, and then group 2 will be your alkaline earth metals, and then you have your transition metals here in between, and then the yellow part, some, other metals. So whenever they say your cation, okay, the one that goes to the cathode, okay, just be aware what a metal is, and all of these rather are metals. So please be aware when they say metals, like copper for one. We spoke about copper there. We knew that was a metal. Okay, you'll have other ones like potassium or sodium or whatever, but just know that those are metals so that you know which one is going to be reduced. Okay, and then when you look at the table of the standard reduction potentials, so there's table 4A and there's also table 4B. Most people say they prefer 4B. Okay, so again, once you have noted your metal, you'll realize lithium is a metal, potassium is a metal, all from group 1, right? Barium is a metal from group 2, as well as strontium and calcium over there. So you see those carry a negative voltage. Okay, so because it carries a negative voltage, in this regard, the H proton will be reduced, right? Instead of these metals. But if they carry a positive, so we're going to look over to the positive side, your metal, I see silver, Ag. There's also copper. You have copper 2 plus, quite a few coppers there. So I don't know if you can see my cursor, but yes, copper 2 plus, you see that it's actually positive. So this one will be reduced more than, it has a stronger reducing ability more than the hydrogen ion would. So this is the table that you would refer to so that you can see which one will be reduced and which one will be oxidized. And also on the sides here, you see they tell you that this is increasing oxidizing ability. Okay, I would say another word for oxidizing ability, I would say oxidizing agent. Okay, so as you go down in the table, okay, the what do we call this? What did I call these agents? Yeah, well, basically, the process is oxidation, and then I forgot what the others I called it. But basically, as you go down the table, you would know that you are increasing. Okay, your reducing agent there would be increasing. Okay, or rather, oxidizing agent going down is increasing. Okay, and if your oxidizing agent is increasing, it means that actually going down here, your reduction is actually much stronger, and that will actually be why. So there you have the H plus, which has a charge of 0. Okay, and you have copper 2 plus over here that has a charge of a voltage of 0.34. So it will reduce way better than it would hydrogen. Okay, I hope you're actually seeing this. But if you're going up the table, which is increasing reducing ability, meaning your reducing agent, the power of the reducing agent increases as you go up the table. Okay, and in that case, remember, reducing agent goes with oxidizing. So in the negative side, they will oxidize much better. Okay, so we had, I don't know if we can actually see your iodine and your chlorine and all of that. Okay, so you have iodine here, and we said it would oxidize better than the OH. So where do we have hydroxide? Okay, let me see where hydroxide would be in this case. Okay. I'm seeing hydroxide as this is a hydroxide ion. Yeah, so the hydroxide ion is there, but we started off with water. Okay. I think for the one that would be likely to be oxidized, let's just stick to those rules. If you have your group 7 ions, those ones will oxidize better than the hydroxide. But when it comes to the ones that will be reduced, this table will actually help, and you have to look at the metals and see, do they carry a negative voltage or a positive voltage? I think that will help much better. Okay, So let me go back to our page and we'll continue with the electrolysis of water. So with the electrolysis of water, well, basically water is a weak conductor of electricity. Okay, it's a weak electrolyte, basically. Okay, and as it is a weak electrolyte. Okay, so because it's a weak electrolyte, it is a weak conductor of electricity. So you need to do something to it so that it can at least allow, the flow of electrons and electricity to be conducted within it, right? So what we normally do would add diluted sulfuric acid. You know that sulfuric acid is actually a strong acid if you have looked at our video for acids and bases. So sulfuric acid is a strong acid, but we dilute it, okay, because we don't want a high concentration of sulfuric acid, or else now we have a different, once it starts dissociating, you have different ions in there, and that's not what we want to do. Okay, so you take that water, which is a weak electrolyte, you add diluted sulfuric acid to it, okay, which would make water slightly acidic. And then once it is slightly acidic, then it becomes a beta electrolyte. Okay, so then we can use water then to have electrolysis occurring. Okay, so yeah, that's basically it that I wanted to cover there. I don't want to go into more detail, but yes, you want to get it to a point where the redox reaction can occur. Okay, so it will then become a good conductor. Okay, and once it becomes a good conductor of electricity, therefore redox reactions can occur. Yeah, redox reactions can occur. So yeah, that is basically it. So you have electrolysis for a molten ionic solution, where you know that your cations will go to the cathode to be reduced, and you have anions that will go to the anode to be oxidized. Then secondly, you have the electrolysis of ionic solutions, which you have water that's also like part of this whole equation. You need to decide which one will be oxidized. Okay, will it be the hydroxide or the anion? All right, and which one will be reduced? Will it be the hydrogen ion, or will it be the cation that forms part of the salt? Then lastly, you have electrolysis of water. Now, what is the application of electrolysis? Okay, this is basically, what people would ask, like, why are we doing all of this? Well, first of all, we have electroplating. Okay, so with electroplating, you need to then, what happens is, let's say you want your spoons, your cutlery to be gold or silver or whatever. So you would take, let's use silver for one. Okay, so electroplating, you would take your pure silver. By the way, pure silver is very expensive, so you don't want your cutlery to be purely silver. But also another thing about silver, which is a downfall, is that it's weak. It's not as strong as maybe other metals that have no significant value. So you take your metal with no significant value, put it on the cathode, put it as a cathode rather. Okay, where it will be reduced. And then you have on the anode side, you would place your silver. So what would happen once oxidation occurs at the anode, your electrons will go all the way to your cathode, and your metal that is not of significant value will be coated with silver. Okay, and then you have your cutlery. So that is electroplating. And also we have it for purification of metals. So let's say you are mining gold or copper or whatever, okay? When you mine it, you don't find gold sitting there at the bottom, huddled together, waiting for you to get it. You will find gold and other, other metals that are in this. So we have an impure substance. So this impure substance, within it, you have the gold. And basically what you'd have to do is to purify it. So remember at the anode is always losing mass, whereas the cathode is gaining. So what you would then have is your impure substance containing your gold that you want, at the anode side. Okay, so as electrolysis is occurring, then with the electrons going all the way to the cathode side, you would have actually the gold forming at the cathode, okay, and increasing in mass. And then on the other side, you would have your impure gold, okay, but it keeps losing mass because the pure gold is moving over to the cathode. And the other metals that were also found in that impure rock, whatever you found, they will settle to the bottom, and you'll probably have other what is it, valuable metals that will also be purified in another process. But that's basically purification of metals. Then you have the electrolysis of brine. Brine is basically sodium chloride, not our table salt that we use in food, but another one. Okay, so it's basically used in the chloralkali industry. And basically, what you want to get there, you want to get chlorine out, you want to get sodium out, you want to get hydrogen out as well. That's basically it. You want to get those products. Okay, so again, you're going to use the application of electrolysis to be able to get those products. Okay, I'll explain it in detail. And then lastly, you have the extraction of aluminium from bauxite. So bauxite as well, it is like an impure substance which contains aluminium. Okay, so from there, you'll basically get your aluminium. Okay, so that is basically the application of electrolysis. I think the thing that's common here is the fact that you want to get the pure metal or the pure product like chlorine and hydrogen, and you want to use it for something basically at the end of it all. So I'm gonna stop here with the theory. We've covered it. It's like taking a long time. In the next video, I will be explaining in detail electroplating, purification of metals, electrolysis of brine, and extraction of aluminium. And then we'll get to a question where you actually see like, how am I going to answer this in an exam? Okay, so we'll tune in next time.